We're going to start by introducing Ceri. Hey, get a hot one. We're going to start by introducing Ceri and Dirk, abusing Windows Hello without a severed hand. Give a good hand for Ceri and Dirk.
Good afternoon, everyone. So my name's Ceri. I'm from Wales in the United Kingdom. So my background is in software development. I was in that world for around 18 years within the DRM and security solution space. And back in 2019, to this very DEF CON week, I switched over to cybersecurity and joined Pentest Partners. So I've been dedicated to red teaming and offensive security for the last 3 years, and have spoken at DEF CON last year and various B-Sides events as well. And I am authored several tools on GitHub, mostly on the offensive security side, but one or two on the defensive side as well.
Hi, so I'm Dirk. I'm just gonna put this down here.
Yeah.
We're gonna leave that one there where it is. So I'm Dirk Jan, second time DEF CON. I've given a talk at quite a few conferences, started at making Active Directory tools, slowly switched to the Azure AD space, which is now called Entra. I have a blog, I have a Twitter account, but mainly excited to be here and show you our latest research on Windows Hello. So Ceri will take the first part, and then I'll come in later, and we'll basically talk you through all the nice things that we did in the past couple of months.
So as Dirk Jan said, the talk is in two halves. So the first half is a focus on abusing Windows Hello from a privileged perspective. So we'll go into sort of Windows Hello containers, protectors, and keys. I'll do a quick tool demonstration of the tool that was released as part of this research, and then we switch to sort of attacks that you can do from an unprivileged perspective, which Dirk Jan will be doing then. So what is Windows Hello? It's Microsoft's passwordless technology. The ethos behind it is sort of two key pairs that are generated when they're enrolled either for the operating system when you log in. It can also be used for passkeys, and even third-party applications can enroll Windows Hello key pairs. So in terms of the differences between Windows Hello and Windows Hello for Business, there aren't any in a technical sense. The only difference is that Windows Hello for Business is a focus on certificate-based authentication to Active Directory, whereas Windows Hello is more sort of consumer market. So we'll start with key storage providers. So Windows has got a common API for dealing with cryptographic operations, and they are called key storage providers. So some examples of the ones that have existed for many years, there's the software key storage provider. So as the name suggests, the keys for this particular provider are all generated in software. So if you do have system level access to an operating system, it means that you can exfiltrate these keys. Then you've got the newer platform key storage provider, and this is for machines that have TPM, and the Microsoft Smart Card key storage provider, which obviously is for storing private keys on smart card. So the KSPs, they design for general cryptographic operations, so encryption, sign-in, key agreement, that sort of thing. And Windows Hello is no different. They've implemented a KSP called the Passport Key Storage Provider. So the Passport Key Storage Provider is split into sort of two privileged services. You've got the NGC service, which is where the applications communicate with over an RPC interface. And then the NGC service will communicate with the NGC controller service. Now, this particular service is tasked with storing all the metadata associated with any enrolled Windows Hello keys. And that metadata is stored within local app data, Microsoft NGC for the local service account. And you do need system level privileges to access that particular folder. So the the Passport Key Storage Provider is essentially a proxy actually for the existing key storage providers that I just talked about. So it doesn't actually implement any of the public-private key operations itself within the passport key storage provider. It essentially proxies it and offloads it to the KSPs. Now, each user is enrolled within a container folder. It's a GUID there that you see on the right-hand side image. So every user has their own unique container folder. And within the containers, then you have a collection of protectors, the key metadata, and various bits and pieces like that. So breaking down into containers themselves, so they're all the metadata is split across these DAT files. Generally, most of them are Unicode strings within them. So as an example there, you can see 1.dat contains the user security ID. 7.dat contains the backing key storage provider for this particular container, which is either TPM backed or software, depending on if a TPM exists or not. And then you've got 9.dat, which stores the Azure recovery key, which we'll get into that a little later on. So protectors, these are your Windows Hello authentication methods. So more commonly, the bioprotector, which would be your face or your fingerprint method of authentication. And of course, you've got the usual PIN that you enroll with Windows Hello as well. And those protectors, they have a file called 15.dat, and this is where a set of intermediate pins are encrypted. Now, these intermediate pins are the same across all protectors, but of course they are encrypted differently depending on what protector was being used. And the intermediate pin is split across a signing pin, a decrypt pin, and what I believe to be an external pin, which again, we'll touch on that in a bit. Now, there are 5 known protectors, and each of these gets a folder within the container folder itself. And the folder name is actually based on the ID. So number 1 is the PIN protector. Number 2 is the bioprotector, which covers both face and fingerprint. And then you got the number 3 is the Azure recovery protector. I've never seen references to number 4. They don't seem to be in the symbols for Microsoft, so I'm not quite sure what happened there. So they skipped straight to 5, which was the pre-boot protector. And then you've got number 6, which is a companion device protector, but that was deprecated in Windows 10 version 20.004. So we start off with the PIN protector. So the PIN protector can be both alphanumeric and numeric, but by default, it's numeric only. So you have to actually click a checkbox to say that you want it to be alphanumeric. But if it is numeric, inside 7.dat, it actually stores the PIN length. And this is why that once you've got the correct PIN when you're logging in with Windows Hello, it will automatically log you in without pressing enter, and it knows that based on the PIN length that is stored. 1.dat again just contains the backing key storage provider that's used for encrypting the protector, and then when it's using the software KSP, 2.dat contains the software key storage provider key ID that was used for protecting the biometric data. So Teal from the insecurity.be website, they've done an excellent blog on this, and I do highly recommend you take a read of it. So this is the process of how the PIN protector is decrypted during a software-based approach. So that area in red there you see is DP API NG encrypted blob. There are sort of articles on the web already that cover the internals of DP API NG. But what basically happens is the user enters in the PIN, that goes through a PBKDF2 key derivation function, along with the salt and the rounds that comes from the CNG key that gets stored as part of the software KSP. And that eventually will return you a private key, and a separate RSA private key that is actually used for decrypting the intermediate pins inside 15.dat. So moving on to TPM-based decryption, as you can see, it's a lot simpler. There's no key derivation function going on or anything like that, like the software version. All that happens is the PIN is entered, it gets converted to hex, and that's what's used to unseal the 15.dat intermediate pins. So the 2.dat is no longer present in that scenario, and that's because there is a fixed key ID that it uses every time, so it doesn't generate a new one. So what type of abuses can we do with the pin protector? So when it's TPM backed, it's actually fairly robust. The biggest risk, I would say, is 4-digit pins can probably be brute forced within around 70 days. Based on the anti-hammering technology within the TPM, it basically slows down any brute forcing. So a 4-digit pin would take about 70 days. But if we move over to a software-backed pin, that's when you start to get in trouble. So there's a hashcat hash that already exists within Hashcat that you can generate, a Windows Hello-based hash. But because we now know the length of the pin as well, we can make a targeted mask attack when you're decrypting it. And with a decent, or modest rig, I should say, 8 digits can be cracked within seconds, and up to 11 digits you can still do within days. And thanks to the Windows Hello 2 Hashcat project for that inspiration. So moving on to the bioprotector. So one thing you will notice on the bioprotector with that red section up the top right, there is no input from the user, and that includes any of the biometric readers. And that's because the biometric protector is not actually protected by biometrics at all. It's actually protected by the system DP API key, which means that once you've got a system level compromise, you can basically reverse those 3 intermediate pins and bypass the biometrics altogether. So the encryption for this is based on the Windows Vault credentials. Again, I won't go into too much detail of the Windows Vault and how them credentials are protected. Lots of articles already out there. But what basically happens is you decrypt the secret within the Windows Vault. That gives you an AES key that is then used for decrypting the 15.dat, which gets you the 3 intermediate pins once again. So onto the recovery protector. So you'll only see this under Windows Hello for Business scenarios. And if the tenant has enabled the recovery capability, it allows users to reset their PIN without destroying all the enrolled Windows Hello keys. If you reset the PIN without the recovery protector in place, basically any enrolled key pair through Windows Hello will then be destroyed, and you'd have to start from the start again. So how does the recovery protector work? So the 3 intermediate pins are first protected with the system DP API key, and then a public key is fetched from cred.microsoft.com/get encryption key, and that encrypted DP API blob is then encrypted once again. But for some reason, Microsoft decided to store the encrypted blob inside the top level container folder as 9.dat and not inside the protector folder. So again, I don't know why they've done that. So the reverse process of getting at the intermediate pins with a recovery protector, there's a post call that goes to cred.microsoft.com/unprotect secret. And the access token for that does require both the NGC and the MFA claim. So what that basically means is when you're going through the reset process, you have to authenticate to Entra, but you also have to go through the process of doing your MFA. Otherwise, you can't decrypt the blob. That's got its own client ID specific for the Microsoft PIN. Again, 15.dat contains the intermediate pins. 4.dat contains the AES IV that's used to decrypt it. Now there is a 9.dat inside the protector folder, but I don't really know what's in that folder. Again, they shifted the contents of the encrypted data in 9.dat within the container folder. So here's an example of the decrypting process for this particular protector. You'll see the protected secret there on the left. And then that's the response you get from the Microsoft server on the right. And those with the BDI will notice that base64 encoded data looks like the DP API common header that you get. And then the system DP API key is used to decrypt that secret you get back, which gives you the 3 same intermediate pins. So the pre-boot protector, I haven't done a lot of research in this area yet, and I believe it's for scenarios where you're going from BitLocker straight to desktop so that you don't need to enter in your PIN. And the most likely scenario is that 15.dat is going to be protected by BitLocker. But there's more research needed in that area. And then the companion device protector was originally intended for IoT device scenarios. An opaque blob in the documentation is sent to the IoT, but what I believe is that opaque blob is the intermediate pins, and that companion device protector is designed to encrypt it. But no real research needed in this area because it's been deprecated and I've never seen it in real life. So a quick protector recap. So protectors encrypt 3 intermediate pins. They're all the same pins across all the protectors. Now the inputs to the protectors do differ depending on what the protector type is. Bioprotectors don't actually need biometrics to decrypt them. And the pin protector is actually extremely vulnerable when there's no TPM present. So what is the purpose of these intermediate pins? Well, they are designed to unlock the actual enrolled keys within Windows Hello. So once you have access to these intermediate pins, you can forget all the protectors, you no longer need them, the pins stay constant for the duration of that container. So there's 4 types of keys that I've come across so far. So the vault key is uses the decrypt pin. The only scenario I've seen that used is the consumer scenario where the local account password is encrypted and then it reverses that then and gets the decrypted password once the PIN is entered. But it doesn't get used in Hello for Business scenarios. Now the Entra pin, the Entra key is enrolled during Windows Hello for Business, and that uses the sign pin. And if you're enrolling for Passkey enabled websites or FIDO based websites, that also uses the sign pin. And then this is what I call the external pin. And the external pin only seems to be used with third-party applications. So an example of this is the key that gets enrolled for OctaFastPass. To use that particular key, you use the external pin. So once again, the keys do leverage or proxy the encryption and decryption or the signing operations to a back-end key storage provider, and that will either be software or TPM, which means if it is in software, you can actually extract the Windows Hello key and take them away and use them off the device. The keys also have metadata files, and there are some common metadata files across all the key types, but then some of the keys have specific DAT files for that particular key. So as I mentioned, the vault key is used for recovering the plain text password of a local account, but that's only under the Windows Hello scenario, not Hello for Business. And again, Teal from Insecurity has covered that in detail, so I do recommend you take a look at that blog. So moving on to the passkey enrolled keys. So 7.dat contains CBOR encoded data. Now I've never come across this encoding format before, so a good shout out to Ace Bond who managed to spot that on Twitter, or X, whatever you're calling it these days. And then once I checked what CBOR is used for, of course it was WebAuthn, so that's what gave me the hint that it's used for passkeys. And then inside, so onto the CBOR encoded data, that which is inside 7.dat, that contains the relay party ID, the user ID, username, display name. But one other important aspect to WebAuthn is the credential ID, but they don't actually store that because that's actually a SHA-256 hash of the public key itself, which is, you see that green area there in the middle picture. And then 11.dat, for the ones that do know a little about WebAuthn, during the attestation, during the login process of WebAuthn, it has a sign count that gets incremented every time, and the relay party backend generally will check that sign count to make sure it's incrementing as expected. So what sort of abuses can we do with passkey? So navigator credentials.get is the main function within browsers that allow you to do an assertion with WebAuthn. So you can actually hijack that particular function and then proxy the assertion request back to a compromised host. So that way then you'll be able to use those WebAuthn enrolled certificates and log into WebAuthn-based websites. And because we can use the key directly without the need of Windows Hello, we can fake the user presence and return that assertion back to the relaying party and log in. So on to the Entra key. So this is enrolled during Windows Hello for Business enrollment. Lots of research already in this area, including Dirk Jan's great work. But basically, you use this key to sign the PRTs that are used for requesting a credential to Entra. And there are features where you can then get the TGT or the cloud TGT and authenticate to Active Directory locally. And again, this particular key pair uses the sign-in pin from the intermediate pins. And the key name, which is inside one.dat, is made up of the tenant ID and the user ID. So on to Entra key abuse. So we can now, with this research, you can directly use the Windows Hello Enroll keys along with the transport key to request a new PRT on a compromised device. So you no longer need to try and extract the PRT from Mimikatz. And one other aspect that's come from this research is the return of Dirk Jan's CV that he reported to Microsoft for the key derivation function version 1, where you can take the random context and the derived key and then use it away from the device to sign new PRTs. So we did report this to Microsoft, which obviously they did say they have fixed it with the release of key derivation version 2. But as they did come back and said they've also deprecated it as well, and they said it will be deprecated during August of this year.
And with that, we mean that we tested this half an hour ago and it still worked. So.
Okay, so a quick introduction to the tool itself that came out of this. The tool is called Shemai, and the reason it's called Shemai is that's Welsh for hello, which is where I come from. So the features of the software allow you to enumerate all the Windows Hello keys that are enrolled on the device, and that's across all the users. Any keys that are using the software-backed key storage provider, you can dump and extract and then use them away from the device. It also dumps the the hashcat hash that you can then try to crack offline. It has the PRT authentication module so that you can do the Entra-based abuse. A WebAuthn proxy module, which is the browser functionality. And I will get to integrating Okta FastPass eventually, just haven't quite got there yet. So a quick demonstration. Let's see if it's going to work. So what you see here is on the machine on your right, so there's two virtual machines here. So the machine on your right is your compromised machine running the Shemai tool, and the machine on the left is the attacker machine that is looking to sort of abuse that Windows Hello based key. So we set up the key to be listening. Just get the IP address for the compromised machine. So we go back to the attack machine. We're just going to create a new incognito window to show no cached credentials. Stick in the compromised host address. And then once you hit save, that will enumerate all the enrolled WebAuthn keys. So you can see Amazon, GitHub, WebAuthn.io. So you click on GitHub, that will take us to GitHub. We go to the sign-in option. We use the sign-in with passkey support, proxies it across, and you're logged in.
All right, thank you. So this tooling is something you can do when you have like full level access to a computer. So if you're a system on a device and you can steal these kind of things, use it remotely, etc. And at this point, we're also going to take a step back because Ceri was mostly talking about system level access. But there's also a lot of things that we can do if we have regular user access. So all of these scenarios that we're going to cover are basically relevant if you have like some malware beacon running on the device in the user session, if they left their device unlocked, etc. And we're mostly going to cover like how this works with Entra or the former Azure AD. And I'm going to assume a few things here. So I'm going to assume that you're all familiar with primary refresh tokens, because if I have to explain all of this, then we're definitely going to run out of time. So we are going to talk about primary refresh tokens and especially how these are used with Windows Hello for Business. So primary refresh tokens, they are just single sign-on token. So you can sign into anything that's cloud connected with them. Now Windows requests these basically by sending a specific request to the token endpoint in Entra. And then it's sending a JSON Web Token. And the reason that it's sending such a JSON Web Token is that these JSON Web Tokens are essentially signed with the certificate of the device. So Entra can see that this request comes from a legit device that is already known to Entra, and that we know that's a trusted device in our tenant. And this will also result in the primary first token keys being tied back to our device, being tied to the TPM if we have one, so it's all basically end-to-end secured. If we are using Windows Hello keys, then we will see a specific payload. So if you use like regular username password authentication, it's going to send the username password to request a PRT. But if we use Windows Hello, it's actually signing some data with these Windows Hello private keys. So if we look at this payload, we see a couple of interesting fields. And the most interesting here for our attack is this nonce value. So this is something that you'll see with a lot of Entra operations, that there's always a nonce involved. And the whole reason for this is that these nonces are essentially time-bound. So the presence of this nonce, which will expire after 5 minutes, means that after 5 minutes I cannot just replay this request and get a token again, because then I would need to get a new nonce. And especially if it's tied to hardware, that means that we actually need to have hardware, access to the hardware of that device to create the signature, and that we cannot just like copy it offline and send it from elsewhere. We also see the username that we're authenticating to, and we also see the assertion field. And this is actually another JSON Web Token. So we have a JSON Web Token inside a JSON Web Token. And this is the assertion. And this assertion is actually signed with the private key from Windows Hello for Business that we also saw earlier on the operating system. So this is the JSON Web Token that is signed with a specific, with this private RSA key. There's a specific key derivation algorithm going on here. And in the payload, we see a couple of fields. So we see the issuer, which is the username. We see the audience, that's our tenant ID. And we also see some timestamps where it was issued again against replay attacks. So there were a few things wrong with this, which is also why I said that this is the old version, essentially. But the problem is that this assertion is generated with our Windows Hello for Business key. And it turns out that if we want to use this Windows Hello key from the user session, then we can just politely ask the operating system to sign it for us. Because it turns out that basically if we call the passwords key storage provider, then we don't need to enter any pins. We don't need to enter or prompt the user to approve anything, because the keys are essentially cached in your session after you already signed in with Windows Hello for Business. So if you sign in on a website and you use Windows Hello for Business to sign in, you'll see a pin pop up. I'm not sure why that's there, because the key is already in your session. The intermediate pins are already cached in your session. So if we just ask the operating system nicely to sign this assertion, it will do so for us without requiring any admin rights whatsoever. We do have to use the native encrypt methods, because C# doesn't expose these methods by itself. The software RSA provider only accepts software keys, not TPM-based keys. But we can basically generate this assertion ourselves. So I wrote a very, slightly straightforward PowerShell script. And basically, if you just run this, it will grab the key from the key store, it will open the backing private key in the password key storage provider, and simply generate the signature. And this signature we can then use for authentication purposes. Now, if you look at this assertion, there is essentially a small issue. And we saw that in basically the overlaying JSON Web Token, there was a nonce. But here there's no nonce. There's just a timestamp. And the timestamp is an input that we control as an attacker. So if I can ask Windows to just sign anything, I can also change this timestamp to be anything. So normally, of course, this timestamp will prevent me from using this after it expired. But if I can change it, I can just put it in a timestamp like in the future or whatever. I can put it like 5 minutes from now, 10 minutes from now. But since it's simply also a time range, so it starts with like when it was issued and when it expired, and it turned out that there's actually no limits on how big this range can be. So this I'm essentially calling the golden assertion. So if you would have access to a user session, then you could just generate this assertion with some simple PowerShell code. And the timestamps, you could just make it as wide as you wanted. So I could just say this was issued like a few years ago. It's valid for the next 15 years. And then that assertion could be used at any point in time because there was no nonce in there that expired. So we could use this assertion to also authenticate in the future. However, there's one little problem, that is that the PRT that we get after this, it is basically tied to the private key of the device. It will be linked with the transport key, and it will also be only accessible by the TPM. So even if we can use this assertion, if there would be a requirement to use it with the same device, it would still be linked to that device on which we maybe no longer have a session. So, sounds like an issue. But it turns out that it is actually not an issue because you can also use this assertion on a different device. And I was really surprised with this. I didn't know exactly why that was necessary. But it turns out that this is needed because you can also use basically Windows Hello keys remotely over RDP. So if you have a device with Windows Hello, you can use Remote Desktop to authenticate to some other device. And it's basically going to use the user certificate plus the Windows Hello for Business private key to also get you a primary refresh token on that other device. So then you don't have to enter any other credentials anymore, and you can just use your passwordless Windows Hello for Business keys to also authenticate on that other device. But it's interesting because our device probably has a TPM, but the other device doesn't necessarily need to have a TPM. So if we RDP to a device that doesn't have a TPM, then it will still use our Windows Hello for Business key, which is protected by the TPM on our laptop. But the resulting PRT is actually not going to be hardware protected. So that means that if I have this machine on the left-hand side, where we see that the key is protected by the platform crypto provider, so it's TPM backed, we cannot just extract that unless we have like some weird downgrades. But if you RDP then to the system on the right, then you see that there I can just simply run Mimikatz, I can extract the PRT, and this PRT is backed by the Windows Hello for Business key on our very much locked down device. So even if your device is very well protected, if you RDP to a device that's not, so if you like RDP to a virtual machine running somewhere in Azure without a TPM that is Entra joined or hybrid joined or some other device that doesn't have a TPM for some reason, you are essentially exposing your credentials because this primary refresh token is a single sign-on token for your account, and it's also Windows Hello for Business based, so it meets like MFA policies, strong MFA policies even. So that's quite a risk basically. And there's no way to limit you from RDPing to non-TPM devices. So this is an issue by itself as well, but we can also use this knowledge to basically work around the limitations. So if we take our golden assertion, we just generate a assertion that's going to be valid for the next 10 years, and we can use that with any other device in the tenant at any point in time. So you can just register like a rogue device, maybe you compromise a different device, you can just use those keys to sign the outer JSON Web Token, and this inner JSON Web Token is already signed based on the Windows Hello for Business keys. And as you can see here in the expiry, it is going to be valid till somewhere 2026, but I could have put anything there basically. So this was reported to Microsoft because this sounded like a vulnerability. So after this, they changed it a little bit. So if you look at the new assertion, then you'll see that there is actually a nonce in there, which means that this inner assertion is now also tied to the validity of this nonce, which is going to be 5 minutes. So basically, it's now also restricted to 5 minutes, and after that we cannot use this assertion anymore because the nonce will have expired. We would have to get a new nonce, which means that we need to calculate a new signature, which means we once again need to have access to that private key. So this was fixed. It was actually fixed in July last year. So Windows at that point included a nonce. However, the problem with this is that even if Windows is doing this new behavior, as long as you don't enforce this, then the whole control is basically useless. So it was actually quite interesting as well, I would say, because in July, Microsoft put out these CVEs, one for Entra, one for ADFS, because ADFS has many of the same mechanisms. And they made a very descriptive, very extensive description of this attack, basically calling like the golden assertion. You can make an assertion, use it on a different device. So they're kind of spoiling my talk a little bit. But the interesting part was that they only enforced this server-side in like May this year. Because if you enforce this before everyone patched, then the old protocol's not going to work and all the devices are going to break. So they put the description online like in July, and they only enforced it in May. So in all the time in between, anyone could have done this based on the description, maybe based on reversing the protocol. But since May is now fixed, and because it's the cloud, it's basically fixed everywhere. So you can no longer make this golden assertion. So as much as I like the name, it's not really relevant anymore. However, there is some remaining things that we can do with this. Because effectively this limits our attack to this 5-minute window, because our nonce is valid for 5 minutes. So we can do it for the next 5 minutes, but not anymore after that. But it doesn't always really matter, because we can still request a new PRT on a different device within those 5 minutes. So then if that device does not have a TPM, then we can get a PRT that's also not tied to a TPM. So you can still do this. You can just not do it until infinity, but you can still do it within the 5 minutes. And as soon as we request this primary refresh token, it's going to be valid for the next 90 days. We can use it for single sign-on to anything that we want. And we can even use this to provision new Windows Hello for Business keys, because it counts as doing multi-factor authentication. We can use this to provision new FIDO keys, basically making our takeover of this account complete. And it is not mitigated by any of the current measures out there. So even if you have like all the new features like virtualization-based security, LSA, PPL, Windows Hello, extended session security, TPMs, secure core PCs, secure AI, whatever, this is basically still possible. So just to see this in action, here I'm again running my PowerShell script. It's generating the assertion. It is now including a nonce, so it's not going to be valid forever. And we can basically copy that assertion to my different host. Here I have RoTX as part of RoTools that I'm running, and I'm requesting a new primary refresh token based on the hello assertion with a rogue device that I registered, which in this case is a fake device, could also be like a virtual machine or something. And you see that I get a primary refresh token. I also get a plain text session key, so there's no TPM here, there's no additional hardware protection, and I can also use this to sign into anything, and it's going to be valid for 90 days or until somebody notices this and revokes it. And if we look at the tokens that we receive, then we see that these tokens have the RSA plus MFA claim, which means that this is actually a token that was backed by a Windows Hello for Business passwordless authentication, which means it will also comply with policies that require like phishing-resistant multi-factor authentication. This also complies with token protection policies, basically all the advanced stuff that is that's currently out there. So basically, this all hinges on that fake device. There are some things that you can do to mitigate this. Basically, your strongest control would be device compliance, because if we provision a fake device, it's not going to be in Intune, it's not going to end up being compliant. Of course, there's also things around that. So if we do have a device that we can get compliant, we can do the same thing. It's just more hurdles that you can throw up to prevent people from doing this. You can also monitor for this, so you can see like if somebody registers a new device and then uses that to authenticate with a existing Windows Hello for Business key from a different device. Might be a little bit suspicious. You can also restrict who can join or register new devices, so then you can limit the attacker to using existing devices. Doesn't fully mitigate it, but it does restrict it a little bit. And ideally, also, you wouldn't have any hosts in your network that you allow people to RDP to that don't have a TPM. Because if you do RDP to a system without a TPM, you are essentially exposing these credentials. And there's also some endpoint protections.
Yeah, so going back to sort of the container scenario, the endpoint mitigations that you can use for the abuse that we've demonstrated. use Windows Hello ESS, which is Windows Hello's newer technology. Failing that, physical keys are always better than sort of the embedded enrollment, Windows Hello enrollment methods. If you don't have a TPM, don't use Windows Hello. But you can also create detections based on access to the metadata files within the containers. Realistically, NGC controller service is the only process that should be reading or writing to those files. So if you find that any other process might be reading or writing those files, you can create alerts around that access. So what the hell is Windows ESS to start with? So it was launched in circa 2020, and it's a feature that's needed in the hardware itself, and it's part of Microsoft's secure core capable machines. Now, I've tested a lot of endpoint devices, and I'm still not seeing a great deal of these in the wild. And the main thing that you need is that the SDEV and SDCP tables within ACPI. And that's to do with secure devices that can be accessed via either the face camera or the fingerprint. So I don't know why there's not a huge deal of these devices out there. I do know a lot of the newer Surface devices have this capability. And what actually happens when you have ESS enabled is the first 20 minutes of this talk you can completely throw out the window because they've rewritten all the container structure. So it's all in JSON. All the containers are in one single JSON file. Same with the protectors as well. And you'll notice new processes that are running. So you'll have a bioiso.exe and an ngc iso.exe. They are running inside trustlets within VTL1, which is the same place where LSAS, the isolated LSAS runs as well. Now, I haven't gone beyond that, so maybe I'll be back next year to DEF CON, or don't know. So, so it's the next thing on my list is to look at Windows Hello ESS. So I just want to give a shout out to all these awesome people that was, all these blogs that were also referenced during this research. I know Dirk Jan is not going to appreciate this, but realistically he should be on it there as well, but he didn't want to be on there, so there you go. So there's the two tools. You've got the Shemai and Road tools, and the Shemai will be live soon enough. I'll tweet once it's all live. It's still private at the moment, but Dirk Jan's Road tools is already available. Thanks for listening.